right. So let ZMI correspond to the output of the mth unit in the hidden layer corresponding to the ith input. Okay. This is not the ith component of the input, it corresponds to the vector xi, right. So it is the ith input in my training data of n elements, okay. And I am going to say that and Zi corresponds to the entire activation of the hidden layer for the ith input, okay. That will fine so far. Right. So now we got rid of our, what did we get rid of here? The T, right. So this is what I was saying, in regression GK is linear and typically it is acting on TK, right, and so this is acting only on TK. So this whole thing is, so because we are only talking about regression, I got rid of that. This will make our life a little simpler when we write the gradient. So I am going to take the, basically I am going to use gradient descent, right. So I have squared error, I am going to use gradient descent. So I am going to take the derivative of the error with respect to the single output layer weight, okay. This is a weight that runs from some neuron m Zm, right, to some output k, right. So that is beta, okay. Just this one weight I am taking here, right. I am taking the derivative of r with respect to that one weight, okay. Is the setting clear? Right. So I am taking the derivative of r with respect to a single weight. Here let us just designate that as beta km. Okay. So what will this be equal to? Okay. Let us do it in a slightly simpler fashion. Okay. So I am going to assume that each term inside is denoted by Ri, right, and then I just do the summation over all I, okay. So that way I do not have to write the summation over all I everywhere. So I am going to say this is dou Ri by dou beta. right. If you remember the earlier that what we had, the thing that I erased here, that was just this, right, yi minus f of x into x was what we had earlier, right, but the input in this case is actually zm, right. If you think about what is there on the other end of this weight, right, so the input that comes from here is actually zm, right. So mathematically if you think about it, just zm beta mk, right, so that is what is happening. So essentially that is what you are going to get. So the I indicates that you are considering it only for the ith input, right. So is it clear so far? We just taken a derivative, right, but it's exactly the same computation that we did earlier. The only new thing here is the derivative of gk. Earlier we did not have that because we are assuming that gk was linear. So if gk is linear, this will again vanish. Now comes the interesting part. Now we will just designate some single input layer weight, we will consider that. So I am calling it alpha ml. So how will I take the derivative of the error with respect to alpha ml? So you look at the error, alpha does not appear directly at all, right, it appears indirectly. So what is the best way to do this? Right, I am just using the chain rule, right. So alpha is going to affect the output of the hidden layer, right, and the output of the hidden layer is obviously going to affect the error, right. So I am going to take the output of the hidden layer, right. So I am going to chain it through the output of the hidden layer. So I am going to take dou zm by dou alpha ml and dou ri by dou zm. So one thing to note is that alpha ml is going to affect the output only of zm, right, it is going to affect only zm. So I just need to chain through zm, okay, is it clear? So then let us do each one of these in turn. So this is rather easy. So what is that? We have that already. So what is dou zm by dou alpha m? What if they had been more consistent? Okay, that makes sense, right. So the derivative of sigma, yeah, can you zoom in? So the derivative of sigma times xil, right. So sigma prime of alpha transpose xi plus alpha naught into xil. So that is essentially the derivative of zmi with respect to alpha ml. Okay, this is straightforward differentiation. Okay, if you are having trouble with that, I do not know. Okay. Now is the tricky part. So, I am looking at dou Ri by dou Zm, right. So, what is Zm is the output from here, right, but unfortunately this guy goes to all the output neurons, right. So, Zm can affect the output through all the output neurons, okay. So far there has been a single path that we have been considering, but at this point we really have to consider all the paths of reaching the output from M, okay. So, what we really have to do is look at right. So, Zm can affect Ri through Fk, right. So, the derivative of Fk with respect to Zm and the derivative of Ri with respect to Fk, that is a chain rule again. So, I have to do this over all k because I can have multiple paths of reaching the output. Okay. So, what is dou Ri by dou Fk? Dou of k by dou Zma, you should be able to rattle it off. Right, that is the derivative of G k. So, putting everything together I can write that is a big expression and I did nothing. So, I just took this and wrote it here, I took that and wrote it there, okay. I just took the product of the two terms, okay. So, what we will do now is just to introduce certain simplifying notations. Right, so if you think about it, I have made my job a lot simpler. So there is this term delta Ka which I have defined. So dou Ri by dou beta is essentially delta Ka into Zmi, right. Dou Ri by dou alpha ml is essentially Smi into Xi. Right. That is the delta part, right, and then you have a beta, and then you have your sigma prime. So this all put together gives me my Smi, right. So I have done nothing, I just applied chain rule and done some manipulation to simplify this, right. If you go back and do it again, okay, you will find that it's very straightforward gradient computation, okay. But it took people a couple of decades to nearly a couple of decades to realize that they could do something as simple as this chain rule, and apparently this technique which is very popularly known as backpropagation. So why is it called backpropagation? So when you take the input, right, and you compute the output, right, you are propagating the values forward through the network, right. But when you are updating the gradients, so if you think about it, so what you are doing is first you are computing the deltas, right, and then you are propagating the deltas back through the weights betas, right. So essentially what you are doing is delta times beta, right, like when you are going forward you do x times alpha and z times beta, right. So here likewise you are doing something like delta times beta, right. So this is something like a back propagation of this delta term through the weights so as to update the first layer weights, right. So that is why it is called back propagation, okay. So the forward thing is whatever you do, this is the forward pass, okay, and the equivalent backward passes are given by that, right. So the actual equations are right. So we still left some things in there. So we left a g prime and a sigma prime and so on and so forth. So if g is your linear function, great, right. What about sigma prime? If sigma is the sigmoid function, then you can take the derivative of the sigmoid with respect to x, and that is what you will get. And if it is the tan h, right, instead of the sigmoid, if I use the tan h function, then my sigma prime will be 1 minus sigma squared b. You can work it out, but fairly easy differentiation. always people get thrown off by backpropagation, but it is really nothing but differentiation and a lot of algebra, right, just manipulating things around, right, it's nothing more than that. So everyone knows the chain rule, right, that's it, it's just a chain rule.